Will you, yes, there we go, camera's on, great. Okay, so welcome back everyone. I guess we've got just a minute before we kick off. There we go, good. All right, let's begin. So it's another great pleasure to introduce Sreeni, Katepalli Sreenivasan, who we know as Sreeni, who's going to talk about some problems of high-Reynolds-number turbulence. So over to you, Sreeni.
Yeah. Thank you, Beverly. I also want to thank all the other organizers for asking me to give this talk. I was greatly looking forward to being at INI, and I'm regretful that the meeting has to be via Zoom. As the subtext suggests, the one in red, the program has a certain philosophical underpinning to it, and I cannot address it by just looking at one problem. So I will look at a few problems, also as an effort to reach out to diverse groups of people in the audience. I'll close with some general remarks beyond the specifics. Since science gains its credibility by being interconnected in some way, a point that will become clear towards the end of my talk, I just want to say that the domain of a small number of particles or a few objects is clearly known to much better accuracy than is available to us. For example, as I mentioned yesterday, the Dirac constant can be calculated by QED to some 10 or so decimal places, all of which agree with the experiment. And so there is a certain clarity there. But let's leave that alone for a while because the field is quite different from ours. But look at an area that is closer to turbulence, the phenomena near the critical point in phase transition problems. The combined success there of the experiment and renormalization theory is such that the constant nu, which is related to the divergence of the length scale. Now, I don't know if there it is, which marks the divergence of this correlation length, is known to an amazing degree of accuracy as shown in this figure. I draw attention to the vertical scale here. I'm quite taken by the precision. You see, there are calculations here and experiments as a function of time. Especially because this is not a very easy thing to do. I happen to know a little bit about it. So I harbor the hope that we too could do as well in turbulence, if only we could march on to higher and higher Reynolds numbers and attain more extensive scaling range, but master all the measurement challenges that come with it. I hope to say more about this later on as well. Despite this kind of motivation and a few valiant efforts that people have made to go to very, very high Reynolds numbers, we have not answered some of the basic questions conclusively. And so I'll discuss three problems. One is thermal convection, and then turbulent energies in wall-bounded flows, and then anomalous dissipation and anomalous scaling. So that's my agenda, and the reasons for uncertainty in each case I will point out to be different, but the general thing is the same. Now let me turn attention first to the problem of the asymptotic scaling of heat transport in turbulent Rayleigh-Bénard convection. I need not tell you what this flow is, but as a reminder, a fluid is contained in a box whose bottom and top plates are infinitely conducting and side walls are not, they are insulated. And the bottom wall is heated and the top wall is cooled. The Rayleigh number, Ra, as I will call it, is proportional to the temperature difference between the two plates, bottom and top, and is the driver for convection.
Sreeni, I'm sorry to interrupt. Should we still be seeing the plot of nu, or should we be seeing?
No, you will get to a next plot soon.
Oh, I see. I'm sorry.
I can get to the new plot now if you want.
I just wanted to make sure we were seeing what you were seeing. Okay. Thank you.
Let's do that. I'm a little ahead of myself now. The Nusselt number Nu measures the amount of heat transported as a multiple of that possible by a conduction alone. And I remind you, not considering the theory and bounds that Charlie Doring, Peter Constantine, Rich Kurzweil, and others have been involved in, and the two paradigms that have survived. One is the Malkus-Spiegel formula, which is given in these references, which says that the Nusselt number is some number which they actually calculated times Rayleigh to the power 1/3. The second is the Kreisman-Spiegel formula, which is given in these two references. Spiegel is in both places and he made important contributions, which says that the Nusselt number is proportional to Rayleigh times Prandtl to the power half. If you're interested in a quick argument about why this half power is possible, you should read this small paper in PRL by Chavan et al. Actually, this is called the ultimate state or the asymptotic state. And Spiegel made this understated plea that the difference between the two formulae is quite striking and its resolution is important. You may remember during the 80s or late 80s and 90s, there was an effort to try to figure this out through experiment. And then we were debating about the 2/7 power law, which was different from either one of them. I've just highlighted the one on top where the Nusselt number goes like the 2/7 power of the Rayleigh number. But that's now no longer a contender for the asymptotic state. Later experiments, which are shown in this slide, now already more than 20 years old, as you can see from the reference at the top in red, show that the 2/7 power, if at all, exists only towards the low end of the Rayleigh number range. And this experiment has 11 orders of magnitude in Rayleigh number, and the topmost Rayleigh number is like 10 power 17. Not exactly geophysical, but almost there. On the face of it, this figure seems to conclusively show that 1/3 power prevails. Indeed, the abstract in another paper that we wrote says something like that. After considering the roles of Prandtl number, aspect ratio, mean wind, boundary layers, sidewalls, and all the other things, we show that the power is like 1/3, more or less. But this work did not end the expectation of the half power law. One reason was that, of course, one could extend the Rayleigh number and say, well, maybe it will get to half power, but that's a difficult one at the moment. The other thought was that, well, we should really have seen it ourselves in these experiments, except that we had the, as we approach higher Rayleigh number, the Prandtl number was not held constant, but it was actually going up slowly. In the figure to the left, the top symbols are the Prandtl number as a function of Rayleigh number. You can see that beyond about 10 power 12 or maybe 10 power 13 or so, the Prandtl number does go up continually. And so in fact, the speculations were made, and that's never written out in print, that if only the Prandtl number was held constant, well, maybe this transition would have been seen already. But actually, if you look at the plot on the right-hand side, which is a theory by Grossman and Losa, which plots the Nusselt number as a function of Prandtl number, each curve representing a different Rayleigh number. The one that's relevant perhaps to us is the one at the top, which is 10 power 15. it is seen that beyond a Prandtl number of 1 or thereabouts, in fact, there is very little sensitivity to Prandtl number. And the red arrows I've seen shown at the top of the figure on the right is really the range that is covered in the experiments. So in fact, there is a good argument to make that the Prandtl number effects are not very large, but it's a kind of a thing, one apology one shouldn't have to make. And so I let things go. Papers in search of the ultimate state, in fact, began to appear over time. And one of the recent ones is by Hay et al., which claims that after transition region of 10 power 13, we found gamma effective, that is the slope, is 0.38 in agreement with the asymptotic state. Whether 0.38 is anything like the asymptotic state or not is not discussing. I'm not discussing it here. But Urban pointed out that under certain circumstances, this kind of change, slight change, is possibly spurious and can be misinterpreted as a transition to ultimate achievement. It's only the result is because the apparatus is quite high and it is really very hard to maintain Boosiness type conditions in, in these measurements. And Charlie, I want to cite him here, not only because I miss him, but also because he made a valiant effort to convince the authors that, in fact, the conclusion was not justified by their own data. Now, so we decided to make some large-scale simulations, which we wrote down in this paper. We had a lot of computer time and big machines, and we went ahead and tried to get as high a Rayleigh number as possible. But even there, even though we had huge computing power, we went up to 10 power 15. We could only do it in a slender cell like the one that is shown on the right. Now I'll show you some results first and then address the issue of the effect of this severe confinement on the results. So the next figure here shows on the top plan views of the temperature field for 3 different Rayleigh numbers increasing from left to right. You can see that at higher Rayleigh numbers, the temperature field is really very fine. And in fact, the scale there is much, much bigger than, let's say, the horizontal dimension of the apparatus. This plot here, the bottom left plot, shows the Nusselt number as a function of Rayleigh number. And to the right is given the fit for that, fit for the top part of this data with the red lines. And you can see that the exponent is 0.331 or whatever, with some error bars attached to it. I want you to, so I plotted Nusselt number compensated by Rayleigh to the power 1/3. And what you see is that in the initial Rayleigh number range, there is probably a different power. There is a different power from 1/3, probably 2/7, as was known for a while. But it is 1/3 beyond about 10 power 11 or so, and doesn't show any tendency to grow further. Compare the details of this with the Marcus-Spiegel result, which gives you this number and the exponent of 1/3, and also the earlier experiment, experiment that I had shown earlier. And so, at least for this slender cell, there is no transition to the ultimate state. The obvious and legitimate objection to this result is that the aspect ratio is small. Of course, many studies made have a small aspect ratio as well, but not as small as the one I've shown. It's a very valid point, and so I'll make two comments which may be useful. First, in this paper, which I just shown here, appeared not very long ago, we made various comparisons of the results with those from higher aspect ratio and found that the situation is indeed different at low Rayleigh numbers, but the difference disappears as we go to higher and higher Rayleigh numbers. The second comment is that the transition from the 1/3 to the half power is often thought to be the consequence of the boundary layer becoming turbulent or undergoing transition to turbulence. But the reality is that because of thermal plumes, the boundary layers are never laminar. They're always turbulent-like and become more and more so as you increase the Rayleigh number. For example, you measure the probability density of any of the quantities like the shear stress or the vertical velocity gradient. They have this kind of distribution, just very similar to what it is in turbulence. And you can see this from Rayleigh numbers 10 power 10 to 10 power 15 that we covered. So the conclusions from this part of the talk I would like to point out is the 2/7 power is limited to low or Rayleigh numbers, which I think is good. Strong support for the 1/3 power and strong indications of a 1/3 power from simulations for low aspect ratio. Clearly, I should point that out. But what may be important is not the aspect ratio per se, but the thickness, the ratio of the thickness of the boundary layer to the horizontal extent of the flow. And in this case, because the boundary layers get very thin, the ratio of the boundary layer thickness to the horizontal dimension is about 1/1000. And so it really does not confine the boundary layers that much, although the outer flow is constrained. Perhaps what matters is the ratio of the thermal boundary layer thickness to the horizontal dimension. I say perhaps. And the half power does occur in other situations. For example, when the apparatus is open on both ends, so you just have a stream of fluid going up and down, or when the boundary layers are absent, as was artificially created by Losa and Toshi, or when the flow is heated radiatively. This is a very beautiful paper that appeared in JFM, also in PNAS. Maybe rough boundary layers will do it, I don't know. So do we know the ultimate answer to the question of whether we have half or 1/3 power forever? Probably not, at least not yet, but we will know soon. The point is, this is a source of frustration for me as well. There is no answer that everyone seems to agree on at the moment. So let's leave that for now and go to the law of the wall in the turbulent boundary layer as another illustration of why it could be frustrating. I'd like to say something about this, which is what Ivan talked about yesterday. That is, flow near the wall, when normalized by the wall stress and viscosity, everything scales in Reynolds number. Yesterday, Ivan showed that it works well for the mean flow, at least to logarithmic accuracy. That is, you plot a whole lot of things on logarithmic scale. Others have also worked on this, like Peter Mankiewicz and Hassan Naguib and others, and they also have come to similar conclusions. So the concept holds true, law of the wall holds true. It must also hold for every other quantity near the wall. In particular, the peak of the fluctuations near the wall must also obey the same general invariance when normalized by wall variables. Something like this is what you would want, which is what you can get from one of the models. But the reality is quite different, as this figure will show. You can see in this figure, the red arrow pointing out to the fact that as you increase the Reynolds number, the peak value is going up, unlike what the graph on the right, which is the kind of modeling people have used, shows. Now, this, of course, has to be accounted for in some way. And these authors just wrote down like this. Instead of normalizing everything by the wall stress, they normalized it by wall shear velocity and a quantity called UE bar, which is a non-scaling external velocity. That is the peak value of the U prime bar will go like logarithm of the Reynolds number. By the way, Ivan mentioned another argument in support of the logarithmic behavior yesterday, constructed on Townsend's attached ready hypothesis. Now, of course, if you allow the logarithmic trend to persist forever, this cannot really be in spiritual agreement with the law of the wall. So somewhere this increase has to break down and it has to become a constant. And that means there's another Reynolds number which marks another transition to something else. And that is something I really do not know what it is. So instead of calling into question this law of the wall or anticipating another transition in turbulent boundary layers, Chen and I provided an alternative argument, and I will present that to you and discuss what it may actually mean. Now, basically our argument was like this. In the wall layer, the Reynolds stress term plus the viscous stress term is identically unity at high Reynolds numbers in infinite Reynolds number range. And this makes the asymptotic value of the maximum production, which is the product of the two essentially. When the sum is bounded like this to 1, the product has a maximum at quarter when both of them are half and half. And that's also the asymptotic of the maximum dissipation. At any finite Reynolds numbers, there is a defect dissipation. That is, the dissipation doesn't reach quarter in these units, but it is a little bit less. And the quarter minus the measured dissipation is this defect dissipation, which you write down 1 minus quarter minus the actual measured dissipation, going like Reynolds number to the power minus m, whatever that m is. In this paper, we presented arguments, which I will not want to take you through, that says that this m is a quarter. So essentially, you have a defect law that says instead of continually increasing logarithmically or otherwise, it will just slowly asymptote to the infinite Reynolds number value. The consequence of that for velocities is shown here. On the left is the logarithmic fit. And on the right is this defect fit, which I just mentioned. And you really want to be conclusive, you need much higher Reynolds numbers, perhaps like the one shown on this plot to the right in the SL test measurements in the desert that were made. But unfortunately, the range of data for the highest Reynolds number, this is on the desert, covers such a huge range from different realizations to another that it is very hard to be conclusive about it. I can draw an elephant between the top and the bottom of these symbols. So one hopes that this Reynolds number range will be covered by the wind tunnel that Ivan had been proposing yesterday, and we'll get data that will tell us whether which one of them is right and or maybe something else altogether. So in fact, you can do a little better. And that is, you can extend this defect argument to other quantities where phi is a quantity, any quantity that peaks inside this, wall layer. And I have this paper, we considered all of them, and I show you a few of them. And the logarithmic law is shown by straight lines here, and the curve really show the defect law. In fact, I can make one more point. So far, I looked at only second order moments. I can look at the other order moments, second, 4, 6, 8, and 10. And you plot them all as a function of distance from the wall. You can see that the bottom one corresponds to u prime squared. The top, the middle, the next red one is u4 to the power half. That means it has the dimensions of u squared, etc. And Ivan and Charles Menevo had this formula, which shows also a log relation, as shown here. But in fact, the defect relation also gives you a similar relation. And the plot in the top simply is a collection of the data available and a comparison between log and the defect formulation. My goal in taking you through all this is not to harp on the slight agreement in the fits themselves. I mean, it may be good in some cases, maybe not as good as you desire in some others. Rather, it is to focus on the fundamental differences of the underpinning philosophies. The unchecked log increase, as I already said, clearly violates the law of the wall. It may stop that behavior at some Reynolds number and become constant, but then we have to contend with a new transition of some sort, which I know nothing about. The defect law simply says that this constancy is restored, the limit of very large Reynolds numbers, and it doesn't require anything new in terms of physics. Which of this really holds and will change our qualitative understanding. At the moment, one cannot be 100% certain, and I hope we will be able to figure that out soon. So again, a lot of work has gone into this, many years of work actually, but still we are at a stage where things are not completely clear. So all available data, as a matter of conclusion for this part, are consistent with the defect law proposed. If so, law of the wall is in no jeopardy whatsoever. For this to be a final word, we need the data at higher Reynolds number, perhaps 1 decade higher. Repeating data over the same range of Reynolds number in different labs, like Ivan did in his wind tunnel, would be highly worthwhile. That's that. Now let me talk about a new wrinkle on the zeroth law, or the dissipative anomaly, which I think is of interest to a number of people here. Peter discussed this, and some of the remarks that Laszlo made regarding Onsager's theorem, as he called it, also relevant. So this was the first experimental evidence for the dissipative anomaly, although the idea had been around from G.I. Taylor, Kolmogorov, and discussed very nicely in Bachelor's book and so on. While for low Reynolds numbers, the suitably normalized dissipation depends on the Reynolds number. And at low Reynolds number, in fact, you can create a little theory for it. As I did in this paper, I've shown the 1984 paper. Beyond the Reynolds number of 60 or whatever, it becomes a constant. This is the essence of anomaly. Even when the symmetry breaking parameter, that is the viscosity, tends to 0, that is the Reynolds number tends to infinity, one has finite dissipation. And these data were acquired in wind tunnel and grid turbulence, like this picture shows by Naguib and Clark. So we measured the energy as a function of distance from the grid after a certain distance. And that gives you the energy dissipation and the rest of it. And so that's how it was done. Now, in that same paper, I had noted a number of caveats to this plot, most of which arise from the length scale estimates in grid turbulence. So I took a look at the DNS data a decade or so later, and that is shown at the inset. In fact, the inset has some of Javier's data as well. The same quantity on the vertical axis and the Reynolds number on the horizontal axis. And I concluded that it was this anomaly was intact. However, if you look very closely, you can see that in the simulations, there is a a slightly drooping trend. It's really not exactly constant, but it probably droops a little bit. I was concerned that the resolution at higher Reynolds numbers was not adequate, so I constructed an artificial spectrum with the knowledge I possessed at the time, and recomputed the energy dissipation and satisfied myself that the conclusion was feasible. Recently, however, of course, more measurements have come into being. Canada et al., which everybody knows about, and Donzis and Young. If you expand et al., you will find my name as well. And more recent data in bigger boxes. All of them showed essentially the same thing. But in fact, the last few points are always drooping down a little bit. This is a cause for some concern. And Theo Drivas noticed an old result that I had somewhere in my papers. And that is the third order structure function with the modulus on the velocity difference, like the first quantity I've shown in this statement in magenta, scales with a slightly larger exponent than unity, which is what the third order structure function would do, which is the quantity shown on the magenta to the very right. And Theo and Greg Yang showed that this implies that the normalized dissipation slowly decays in Reynolds number, perhaps as a power law. Call it weak anomaly. Greg was not that concerned about this. He said, well, weak anomaly still implies that the velocity differences go to infinity. So it's really not something that one should be worried too much about. But to me, it worries a lot. Is it really going to zero as you go to higher and higher Reynolds numbers, however many decades you have to go? Or does it really asymptotic constant? It may be maybe not important for some people, but it is really important for me. It turns out that the precise manner in which data are forced in the simulations does make a difference. And in fact, forcing has been discussed already in some fashion, but maybe not in the spirit in which I'm saying it. So in addition to this immensely large computations we already had with certain type of forcing, we created a new database with a different forcing, which is shown on the right. And we made sure that the resolution was right in many cases at least. And the accuracy there is better because we allowed for many, many length scales in the calculations. Now I plot for you what we learned from three sets of things. In the vertical axis is plotted this quantity normalized dissipation. But notice that the origin is not zero in each case. Now, all of them show the same trend, that there is a small drift towards the end. But the best fit for this is not a power law towards the end. In fact, the power law does change the exponent from one location to another. But a thing like this, it is sort of like the defect law that I showed you earlier. So what it says is that the normalized dissipation D approaches a constant A like the Reynolds number to the power minus 3/2. And this constant A would be about 10 to 15% smaller than what we might have assessed had we not considered this slow drift in D. But there is a non-zero constant of the order unity. This scenario explains the data best. In fact, I show you in the next slide how the defect varies with Reynolds number, and we give you the minus one half power. While I am not certain that this is the truth, empirically like this, nobody can be sure one is approaching the truth. Well, one knows the truth. One can say one approaches it. While I'm not certain, the best scenarios is that the anomalous dissipation does seem to hold in the strong sense in which we always understood it to mean. Let me make one comment on the anomalous scaling of structure functions in the inertial range, because I am talking about anomaly here. And then I close my talk with a few remarks. So from a large number of experiments, and in fact, they were begun by Anselmet et al., which Uriel Frisch discussed earlier. What is plotted is, if you look at the velocity difference shown in the big letters in the figure, raised to the power n, averaged over all possible places, goes like r to the power zeta n. Now, zeta n are the scaling exponents for these velocity increments. And as long as r is in the inertial range, you expect some power law like the one I have shown. It's not a trivial statement by any means, but let's just go on. Now, what is plotted here in the vertical axis is zeta n as a function of the order of the moment n. Now, the symbols here are the ones that have come from a very elaborate work that was done at 2 Reynolds numbers that I've shown here. But I don't want to talk about those elaborate details, but I simply want to say that they are representative, you might think, for the present purposes, of the whole host of experimental data and simulations data that are available, some of which are mine, some of which are others, and so on and so forth. Now, the various lines here are due to different models, and I do not want to talk about that. We'll skip that. The top dotted line is the Kolmogorov line, 1/3, slope 1/3. And the difference between the two, or the deviation, is this anomaly. Now, what I want to call attention to in this plot is the same results for the transverse velocity differences. That is, you take the velocity increments at 2 positions in a direction perpendicular to the horizontal separation vector. So that's what you want to do. And if you do that, normally one would have said everything is the same, longitudinally same as transverse, and there is universality and all this business. But what is new is that the transverse exponents appear to saturate the order of the moment increases. That they are actually slightly different at low order moments from the longitudinal. I knew in 1990s. What is new is this saturation. And there are 2 sets of data, one for Reynolds number 650 and the other for 1300. Whether or not the saturation values are different Reynolds numbers is something slightly more detailed to argue. But the fact that it saturates beyond order 8 or something like that seems real. So let's pause for a moment to understand what the saturation means, because I think it is important, if correct. The implications are described in this paper, which I'm sure you haven't seen. But I will only comment on one aspect of it. First of all, when you take higher and higher order moments, what it means is you're focusing your attention on larger and larger fluctuations from the mean or whatever. These huge fluctuations are represented by a quantity which is shown in blue in the second line, which is delta R u to the power n, average taken to the power 1 over n to preserve the dimensionality. Now, the saturation means that, writing it like the one I have shown here in the magenta, taking notice of the definition, the top line, it says that R over L, the R being the scale and L being the integral scale or something like that, going to the power zeta n over n. If zeta n is constant with n, that ratio goes to 0, and you have, therefore, the whole thing tending to u0. Thus, what is clear is that as R, even for very small r, the velocity differences could be as large as the large-scale velocity u0 itself. You see what it means? It means that the velocity fluctuations, even over the smallest scale, can be of the art of the large scale velocity, resembling a situation like that in shocks. And this has an important practical and theoretical consequence. So if it is like shocks, what it means is something like what I've done. Nonlinearity tries to steepen the things. Normally speaking, what the pressure will do is it will eliminate or obviate these large gradients by um, shifting energy to a different component of the velocity fluctuations. But if there are steep features like this in transverse velocity differences, as the saturation of the exponent suggests, then the annealing effect of this nonlinear steepening by pressure is becoming weaker and weaker for higher and higher velocities. So pressure on the average is incapable of countering the steepening effects, thus renders these saturation possible. Intermittency is the local imbalance between, between these two tendencies, the nonlinearity and the pressure effect, which I think is what Peter was saying yesterday, as one possibility. And this says that, in fact, if you are considering high order structure functions or very high amplitude perturbations, pressure probably does become weaker. Of course, if that is the case, then solving the problem is really not that hard at all. Now, so okay, so let me make a few concluding remarks. I probably still have a few minutes. It always seemed to me that attaining larger and larger Reynolds numbers would get us to a point of greater certainty, but those efforts have brought on all kinds of technological challenges. Temporal and spatial resolution, which is really beyond the Kolmogorov scale, confinement and quality of flow, not just in the convection that I showed, but in wind tunnels and others, grid resolution and forcing of flows in simulations, and all kinds of things. For example, I had thought that with the enormous increase in computing, we would have really nailed down homogeneous and isotropic turbulence in a box by now. But actually what is happening is we have sort of saturated at some level beyond which it is very, very hard to go because of resolution effects and the length of time it takes for convergence and things of that sort. Some of them are technical, there is no question about that, but they are impeding what I would call progress in this sense. But there are also the fundamental reasons why one cannot go very far. So I'd like to illustrate the dilemma that I occasionally face. I mentioned, or I mentioned yesterday perhaps, but I'll mention it now, that we know Boltzmann constant, let's say to 10 decimal places. In practice, I rarely need more than 2 decimal places. But the point is that I know that there is something for real. If I have ever wanted, I know I can go back to it. This is like the core of the apple, which is real. Now, let me contrast it with a situation in turbulence by taking the Kalman constant as an example. I take Kalman constant as an example only because Ivan introduced it so very nicely yesterday, and I don't have to do that. And certainly not a criticism of what Ivan said. So let that part be very clear. So Ivan rightly pointed out that people knew its value to be 0.4 plus or minus 0.02 in the 1930s. And 90 years later, we are still concluding that it is 0.4 plus or minus 0.02. You might really marvel at the consistency, which is probably true, but it also gives a different message. And that message is what I want to convey. If I knew with certainty that it is really 0.4 and changes from 0.38 to 0.42, depending on certain secondary conditions, such as whether the measurements are made in Melbourne or Sweden or something like that. I'm just kidding, of course. Depending on various but well understood factors, I would be very happy. I would be very happy because it would mean that there's a core to the flow, which is whose dependence on other quantities I understand. I would understand that there's a log region for which within bounds a priori known, I fit results in the stated number and things of that sort. Now, if it is the same for all flows, then I know that the outer flow does not make any difference to the inner flow, and that would make me very happy, for instance. If on the other hand, I know for certain that it is 0.38 in boundary layers and 0.42 in pipe flows, then that would make me happy also, because then I know that the outer flow would have some impact on the inner flow, and I would make a model, and we would make some progress. I would give it another talk at INI meeting and all that, but I would make some progress nevertheless. But let's take the situation now. I exaggerated a little bit just to make my point, so please bear with me. If we say that it is 0.4 plus or minus 0.05 or whatever, 0.2, but don't know why this difference arises, and say that it may be because of any number of unknown features, it does not tell me much. I'm sort of unable to make much progress. The situation is a little bit like an onion, as I've shown here. You peel one layer and the other layer also looks the same. The situation is best described by this quote from Laura Acosta, whoever she is. I don't really know who she is. There's a lot to you, like the layers of an onion. Just when I think I have you figured out, I peel off another layer and discover something unexpected. You are complex, and this is a good thing. And this part on the red, that this is a good thing, is the sentiment that keeps me going all the time. But it is the general sentiment that keeps me awake at night and keeps me concerned for the field as a whole. That should concern you as well, and it should keep you awake too. Thank you very much.
Thank you very much, Srini. Very thought-provoking.